By the end, you'll be able to derive an infinite series for square roots and use it to find an approximate value for the square root of a number. We'll begin with two well-known infinite series. Our first piece of the puzzle is the Taylor series for cosine. It states that the cosine of an angle x can be represented as this infinite sum. Don't worry about memorizing it, we'll be using this formula directly. Our second piece is a series for the variable x itself, which is defined in terms of an angle theta and the tangent of that angle. This series looks more complex, but we'll see that the substitution will simplify nicely. The angle theta is restricted to be between 0 and 45 degrees, which ensures the tangent of theta is between 0 and 1. This condition is important for making sure our series converge. Now let's connect these two pieces. Our goal is to find an expression for the cosine of x. We know that in a right-angled triangle, if we label the opposite side t and the adjacent side y, then the tangent of theta is t divided by y. From this, we can also write the cosine of theta. It's the adjacent side, y, divided by the hypotenuse, which is the square root of t squared plus y squared. So, cosine of theta is y over the square root of t squared plus y squared. Let's perform a bit of algebra on this expression. If we divide both the numerator and denominator by y, we can rewrite cosine of theta in a slightly different form. By dividing by y, we get 1 over the square root of t over y squared plus 1. Notice that inside the square root we have t over y, which is just our tangent of theta. This confirms a fundamental trigonometric identity. 1 over the square root of tangent squared theta plus 1 equals cosine theta. We're now ready for the main event, substituting our series for x into the cosine series. But first, let's simplify our notation. Let's define a new variable at d to be equal to tan theta or t over y. Remember, the restriction on theta ensures that d is between 0 and 1, so the series will converge. Now let's take a deep breath and combine our equations. On the left side, we have our expression for cosine of theta, written in terms of d. This is 1 over the square root of d squared plus 1. On the right side, we start with the cosine series, but instead of x, we plug in our entire series for x in terms of d. This gives us a double summation, which might look intimidating, but we will simplify it. Let's focus on simplifying the inner summation. Notice that the entire inner sum is being raised to the power of 2 minute. Here's the inner term we need to simplify. We can factor out a d to the power of 2 miasdas from the entire expression. To do this, we can pull out one factor of d to get d to the power of 2 mis. Then we are left with a new inner sum where each term contains d to the power of 2b. Now we can place this simplified term back into our main equation. Our equation now looks much cleaner. The d terms are more organized. We're getting close to our square root series. The next step involves some clever and slightly non-standard manipulation. We're going to replace d squared with just d. This change simplifies the terms involving d into a more manageable form. This is a common technique in series manipulation, so long as the new series also converges, which it does here because d is less than 1. Making this substitution, d squared becomes d. Our equation now looks like this. We're essentially transforming our geometric variable d into a new variable that behaves in a way that generates our target function. The left side now looks very promising. We have 1 over the square root of d plus 1. Let's rewrite this. By plugging back our original variables t and y, the equation becomes y over the square root of t plus y. Therefore, we have found a complex but legitimate infinite series for y over the square root of t plus y. So when can we use this formula? It allows us to calculate the square root of y by multiplying it by the series we just derived. Here are the conditions. First, y is the number whose square root we want. Second, we choose a number t such that t plus y is a perfect square, and this perfect square should be close to y. Third, the absolute value of t divided by y must be less than or equal to 1. This ensures that d is less than or equal to 1 and the series converges. Now let's look at another, more standard way to calculate square roots using a series. The binomial expansion. This approach is generally more practical. We start by approximating the number we want to find the root of. Let a be an approximate value for the square root of y. Then a squared will be an approximation for y. We can define t as the difference, so t equals a squared minus y. We can rearrange this to get y equals a squared minus t. Now we can write our square root as a function of this approximation. The square root of y becomes the square root of a squared minus t. We can factor out a squared to get a times the square root of 1 minus t over a squared. If we define x as t over a squared, we get a very convenient form. A times the square root of 1 minus x. This is exactly the form for the binomial series. The general binomial expansion for 1 plus z to the power of k is this infinite series. The series involves binomial coefficients. For our case, k is a th and z is negative x. Substituting these in gives us the binomial series for the square root of y. And this simplifies to our final form. The sum from k equals 0 to infinity of a times the binomial coefficient. 1 from choose k a times y over a squared to the power of k. This is a very powerful and practical method. So, which method is better? The binomial series, due to its simplicity, is generally the preferred choice. However, comparing the two approaches is incredibly insightful. We've arrived at two different yet equal series for the square root of y. The complex series from our first derivation, and the more straightforward binomial series. The two expressions must be equal, which is a powerful mathematical statement. This equality itself is a remarkable result, showing the connections between different areas of mathematics, from trigonometry to infinite series. We have successfully derived an infinite series representation for a square root and compared it to the standard binomial series. While our first method was circuitous, it showcased how different mathematical tools can be combined. The binomial series provides a direct and practical way to find square roots to arbitrary precision. Thank you for joining this exploration into the fascinating world of infinite series and square roots.